Now, let us proceed. We have assumed a displacement field u to be minus d delta by dx, delta y by dx to y minus y naught E x plus delta of y as a function of x E y. Okay. Now, I want to compute gradient of u, so that I can compute the strain. Gradient of u is h, which is given by dou u x by dou x. If you recollect, we saw this when we were looking at strains, dou u x by dou y, dou u x by dou z, dou u y by dou x, dou u y by dou y, dou u y by dou z, dou u z by dou x, dou u z by dou y, dou u z by dou z. Okay. This for the assumed displacement field would be minus d square delta y by dx square into y minus y naught minus d delta y by dx 0, d delta y by dx 0 0 0 0 0. Okay. Now, the linearized strain, as we saw before, is given by 1 half h plus h transpose, which in this case happens to be given by this matrix y by dx square to y minus y naught 0 0 0 0 0 0 0 0. Here a few comments are to be made. The first comment is you have only epsilon xx strain as minus d square delta y by dx square into y minus y naught, and there is no shear strain or other components of the normal strain. In effect, what you are saying is there is no Poisson's effect in this problem. That is, if you consider Poisson's effect when there is an axial strain, there will be a lateral contraction that is happening in the other two directions, which are ignoring as a first approximation for the problem. Okay. Basically, what we had was we had only the axial strain, we ignore the Poisson's effect, which means we are ignoring the lateral contraction that will happen when there is a axial strain. Okay, that we have ignored as a first approximation. The second thing is, since we assume plane sections remain plane and normal to the neutral axis, there is no shear strain and there is no angle change in this coordinate system. Okay, there is no angle change in this coordinate system. So, since you have the plane being perpendicular even after deformation to a particular line which was initially it was perpendicular to. Okay. So, that is basically because of our assumption of the deformation field for the beams. Okay. So, the strain is given by this expression, then we appeal to one dimensional constitutive relation wherein sigma xx would be related to epsilon xx through the relation E times epsilon xx. Okay. This is one dimensional constitutive relation because we are ignoring the Poisson's effects. Okay. So, now then sigma xx is given by minus E times d square delta y by dx square into y minus y naught. Okay. Now, what we will do is we will go back and plug this expression for sigma xx the equilibrium equation that we had. That is, we will plug sigma xx in this expression, in this expression, in this expression, and then use this equilibrium equations, this and this, to find what is the variation of sigma xx, basically the unknown function. The unknown function here is d square delta by dx square. So, we want to estimate this. So, we will see how to estimate this. Okay. Okay. So, we saw that sigma xx is given by minus E times d square delta y by dx square into y minus y naught. Now, the axial force P is sigma xx into dAx Ax, that will be E times d square delta y by dx square into y minus y naught integrated over dAx. This dAx is nothing but dy dz, as we have seen many a times now. Okay. This has to be equated to 0. Okay. Now, the integration with respect to y and z, it is independent of x. So, I can pull out d square delta y by dx square outside the integration. So, this will be E times y minus y naught into dAx is equal to 0. Since d square delta y by dx square cannot be 0, identically this will imply that integral E times y minus y naught dAx has to be equated to 0. Okay. Now, let us assume beam is homogeneous, that is E is a constant, implying no spatial variation. Okay. So, I am not considering the case where the beam is made of two different materials, for example, concrete and steel or wood and steel, wood and aluminum and so on. Okay. So, I am considering a case where E is the same throughout the beam, and this also means that E is same in both tension and compression. Okay. This also means that E is same in tension and compression. We will see why I am saying this shortly. Okay. Now, what happens now is, now this has, I can pull out E since E is a constant. So, integral A of x E y minus y naught dA of x will give me now E times y minus y naught dA of x equal to 0. This implies integral y minus y naught dA of x has to be 0, since we saw that E cannot be 0 because E has to be greater than 0. In material parameters, when we estimated the restriction on material parameters, we saw that. Now, this will imply y naught integral dAx must be equal to integral y times dAx, or y naught is given by integral y times dAx divided by integral dAx. Okay. What is this? Integral y dAx divided by integral dAx is nothing but the centroid of the cross section, the y component of the centroid of the cross section. Okay. Y of the centroid of the cross section. So, basically y naught is identified as, this implies y naught is equal to y centroid of the cross section. Okay. Now, we have found what y naught is, or we have found the expression for y naught. Next, let us go ahead and find d square delta y by dx square. Okay. Now, I know that mz moment is given by integral sigma xx into y dA x a of x. This I am claiming is same as sigma xx into y minus y naught dAx Ax, since P is 0. Integral sigma xx into y naught dAx Ax would be y naught into sigma xx dAx. So, that is equal to 0. okay, because just now we showed that sigma xs dAx is 0. So, I can rewrite the moment equation as this. Now, I substitute for sigma xx from the previous equation, that is it is minus E times d square delta y by dx square into y minus y naught into y minus y naught dAx. Okay. So, this is nothing but again dAx is dy dz, this is delta y is a function of x alone. So, I can move that outside the integral, this will be d square delta y by dx square integral E times y minus y naught whole square dAx Ax. Okay. In other words, this is nothing but from here I get d square y by dx square to be mz, which is a function of x divided by integral a of x E times y minus y naught square dAx. Okay. We saw that if the beam is homogeneous, E will be a constant. We saw that if beam is homogeneous, E would be a constant, and hence you get mz of x divided by E times y minus y naught whole square dAx. This is for a homogeneous beam assumption. Okay. So, now what is this? This is nothing but mz of x divided by E times I z z, where I z z is given by integral y minus y naught whole square dA x A of x. This is moment of inertia about z axis and neutral axis, about z neutral axis, direction at the neutral axis. Okay. About the z direction of the neutral axis. So, we get the equation minus E times d square delta y by dx square is mz by I z z. Okay. We saw before that sigma xx by y minus y naught is again minus E times d square delta y by dx square. Okay. So, combining these two equations, you get the beam bending equation which is sigma xx by y minus y naught equal to mz by Izz E into dx square. Okay. So, we have the beam bending equation given by this equation in here. Okay.